So we start with the color scales first. So we have the X, Y, Z values, and I will show you how the HunterLab, CLCH, and CIELAB are derived from the X, Y, Z values. So why did one develop such scales? Actually, it was first Richard Hunter who tried to find a scale that is that would be more intuitive to grasp the measured colors. That's the first goal. Then it should be easy to compare and to communicate color with the scale then. And the last one is to quantify perceptible color differences as equally as possible. So if I have a certain difference qualified by a number, that would give the first similar impression in the blue range as in the red range, for example. So for the entire color space. And you see here, we are already talking about a color space and not a unique scale. So for example, meters, we can measure by a single number in meters. So length, we can measure in meters. But just one scale wouldn't suffice because we can, for example, find a number for red and for blue, but then we have certain other directions we have to take into account. Actually, the first attempt to characterize colors was already done by Albert Henry Mansell, who was an artist in 1900, and he developed this Mansell color system. And there you already see we have different slides in different directions, and you see we have darker colors on the bottom and lighter colors on the top. So this is already representing a kind of a color space here. And actually this Mansell color system is still used in Japan nowadays. But it's it's for visual comparison, of course. That's not a measurement. So we have the 3 dimensions. And what you can see here already also, it's not a spherical shape. For example, here it's going a little bit out a little bit more. So for the yellow and greenish parts, for the light yellow and greenish colors, we have more perception than, for example, for the light blue parts of the color space. And actually, if you want to have an intuitive color sorting, the most intuitive thing what would be done also by children in the kindergarten, if you ask them to sort colors, that is the color wheel with all hues. So you're going from red to orange to yellow to green to greenish blue to purple, and then to blue to purple, and then back to red. So you have all the colors characterized by this color wheel. And actually, this is really the basis of the color space. And we call the kind of color is also called the color hue. And as you can see, there's no such thing as a greenish red or a reddish green or something like that. So these are really opposite colors. You can't go from green to red by another color. The same is true for yellow and blue. There's no bluish yellow or something like that. That would already give green, for example. So that's really a natural way for us to sort the colors. And actually, in addition to the hue, there are other qualities of a color, because I can't only describe it by a hue. For example, I have a yellow, but I can also have a light yellow, that would be lighter, or I could have a darker yellow. So it's rather mixed with black here. And there's a third quality, and that would be the saturation. So saturation would mean how much pigment am I using? And if I show a less saturated color here, it seems a little bit lighter, but actually it's the same darkness here. If I would print these 2 colors in a grayscale, I would get the same gray, but actually that color is more saturated than that one here. Yeah, so we have the saturation as well. So these are the 3 elements to characterize a color: the hue, the lightness, and the saturation. So and this can be represented by a 3-dimensional color system. So we have already in 2 dimensions the color wheel here. And as I said, that's the hue which is represented here. Then perpendicular to that, we have the lightness, which goes from black to white here. And then the chroma or saturation goes from inward to outward. So it goes from a gray to a more and more saturated color here. So for example, from gray to red or from gray to yellow and so on. So we have the 3 dimensions. Okay, so that is really an intuitive arranging of all colors. So now I'm going into the color scales themselves. So people are often confused when they're using color measuring instruments. So you can select either LAB or L star, A star, B star. So short LAB is HunterLab, and L star, A star, B star is the LAB from CIE, the Commission Internationale d'Éclairage, alors from the Commission for Lighting here. And so we have 2 color scales, but why do we have them? Actually, it was, well, just a moment. Now, if I first go into how these LAB span the 3-dimensional color space here. So we have the color wheel, and this is but this is defined by 2 axes. So I have an A axis from green to red, and an B axis from blue to yellow. And so for example, orange would have a part of the positive A axis and a part of the yellow B axis. Orange would be here then. And then by that we have the horizontal plane, and perpendicular we have the L axis again. So that's from black to white. And thus we have the whole color space. We have the L axis going from 0 to 100, from black to white. Then we have the A axis, and that is defined in the way that the positive values will be red and the negative values are green. And the B axis in the way that the positive values are yellow and the negative values are blue. And you can see in the middle at 0, it's gray. And just to give an example here, the origin is 50 because I'm between 0 and 100 here for L, and A is 0 and B is 0. That is a medium gray. And as I told beforehand, so it's not really a spherical shape, but it was easier to show it like that. It's irregularly shaped. And if we look now, for example, at our example with the yellow school bus, if we show this, now the LAB scale, it's easy to understand the color. I have an L value of 67, so 68 about. That means I'm in the upper hemisphere of the sphere, so it's a rather light color. The brightness in the upper sphere. And then we have an A value of about 20, so that means it's slightly reddish. So positive values are in the red area. And a B value of about 60. That means it's clearly yellow. So we have a clear yellow with a light reddish shade, and it's a bright color. So we can easily, from LAB, we can say what color is represented. Is there any question here? Okay. And now, as I told you, we have 2 scales. We have the HunterLab scale. So actually, Hunter was the first one to form this transition from XYZ to LAB. And this is used as LAB without stars. That's the HunterLab scale. And he invented it about in 1948 already. And later on, it was the Commission Internationale d'Éclairage revised the scale and in 1976 and defined the L star, A star, B star scale, which is also called the CIELAB scale. Just to show you the difference, you don't need to understand that, but you can see these LAB values are all derived by the XYZ values, which we measured, which we found last time by the instrument. And we have certain fixed numbers, and these are representing the illuminant observer here. And as you can see, for example, here for the HunterLab scale, we have the square root, and here we have already the third root. So it's a little bit more complicated what did the CIE here. And if we have a look now at both scales for our school bus, you will see it's quite different. Already in the L value, we have a difference of 6 units. That's not very much, but still it's different. And the A values are quite similar. But if you look at the B values, they are really different, of more than 20 units, 25 units. And so you mustn't mix the two scales. You really have to define first which scale you're using, because later on, because if you're talking, the one person is talking about LAB and the other about CIELAB, it's not the same thing. And this is because neither of the two scales is really uniform. So HunterLab is a little bit overstretched in the blue color range, and CIELAB is a little bit overstretched in the yellow color range, because mathematically it's not, it's perhaps someone finds it later on, but until now it's not up to now it's not possible to find a scale which is really uniform in the whole color space. So what do we recommend to use for measurement? That's clearly nowadays the CIELAB scale. That's mostly used, and so you can easily communicate with other companies as well. Okay, that are these two scales here. And now I come to the third scale. This is the CIE-LCH or L*C*H scale. And actually, that's not really different to the other scales. It's just different expression of it. We still have the same color space. And I, again, want to define the yellow color of our school bus. So in the LAB scale, I'm doing it by brightness, an A-axis and an B-axis. So I have these three values, but I can just define it differently as well. I have L, and then I have C as the chroma or saturation. So that is the distance to the vertical axis. And then I give another value, and that is the angle from the red axis. So that is H is an angle, and that is called the U. So you can say at 0 degree, I have red. At 90 degree, it's 90. I have yellow. At 180 degree, it's green, and 270 degree, it's blue. So actually, I think it's also it's a quite intuitive way to tell it. Yeah. And if I compare this, so of course the L value is the same. Here I know how much it's in the reddish area and how much in the yellowish area. And here I can say how much is it saturated. So it's quite saturated here. And H gives me the angle. So I can say it's near to 90 degrees. So it's rather yellow, but it's still in the red part here. Yeah, well, actually, I would normally tend to use this color scale, but as we see, it's rarely used. There's a big advantage. It's intuitive because I have really the brightness, the saturation, and the U. And the same angle H means the same U. So I can really compare more and less saturated color. But as we see, for most people, an angular coordinate H puts them very often off. So they don't like angles, so it's not very often used. Okay, and now if we have a conclusion for these color scales, we can say the most commonly used scale is the C, L*, A*, B* scale.